In this lecture, I introduce some basic properties of systems. The first one is linearity, and the other one is time invariance, and memoryless and causality. These four properties have important physical interpretations, so you need to find a clear idea or clear definition should be understood. So I said that the system transforms the input signal to the output in somehow. So the transformation is presented by these notations. The first property is linearity. A system is linear only if the additive and homogeneous property is satisfied. Here shows that the definition of additivity. The input is added and applied to the system, then it should be equals to the input x1 and x2 is applied separately to the system and add up the output. It means that here are a systems exist here. If we applied x1t, then the output is y1t. Let this one is the first output of this one, and if we applied x2t, then we get a y2t. That's this one. Then if we apply x1t plus x2t, we added the input and applied here, then the output are equals to y1t plus y2t. So that is explained the additivity. If it satisfies these conditions, we call it satisfied additivity condition. The next one is homogeneity or scalability. If we apply the input by multiplying a, and then the output are equals to a times its output. It's similarly explained like this way. If we applied here a times xt, then it should be equals to a times yt. So if it satisfies these conditions, we call it a homogeneity or scalability. If additivity and homogeneity satisfied, then superposition theory are working. Superposition are shown here. Linearity means additivity and homogeneity. See, if both of the additivity and homogeneity are working, then we can use a superposition theory. Here is an example. The first one is a time derivative. A system is time derivative. It means that the xt is applied here, then system is time derivative operator. This is system. Then yt. So obviously yt is a time derivative of xt. Okay. You can check that the additivity and homogeneity. You mean that the x1t is applied to the differential in system, then output will be dx1 of dt. If we applied x2t, then the system output will be dx2t of dt. Then what if apply x1t and x2t added first, and then apply system? Then it will be given like this way, dt plus x2t. So it satisfied the additivity. And what about the homogeneity? Homogeneity means this one, a times x1 is applied, x1t, to the system. This system is just a differentiation. Then we get the a dx1 over dt. So this is this output and just multiplied. this satisfies the scalability or homogeneity. So we call this one is a linear system. You can try to these systems. It means that if we applied xt, that kind of systems, square systems, then output will be given xt square. You can try to additivity and scalability. Both of them are not working. So this one is a nonlinear. And I would like to give one more example here that let's try system yt is 2 times xt. Again, it's 2 times. Then you can try this one. This system, you know that the system can be described like this way. Input is applied here and just multiply 2 times xt. This is the output. Okay. In these systems, if you try this one, so x1 is applied, then output will be 2 times x1. x2 is applied, then 2 times x2. And if we applied x1 plus x2, then it will give 2 times x1 plus 2 times x2. So it satisfied additivity. And what about the scalability? Alpha times x1 is applied here, then 2 times alpha times x1. So it also satisfied. So this is linear. And the last one I would like to emphasize is this kind of system. If x1 is applied here, then output is 2 times x1 plus 1. So you can describe that one into this way. Yt equals 2 times x1 xt plus 1. This kind of system. Could you try this one? If you check up this one, this becomes nonlinear. Because of this offset, if there is no offset, it's a linear, but there is offset, it's a nonlinear functions. So think about the definition of linearity is not depend on the shapes of the function. It means that the additivity and homogeneity. The next property is time invariance. Time invariance means that if input is shifted, then output is just shifted versions. So if this satisfied, if we shifted input applied, then output is just shifted, then we call this is time invariant systems. Here is an example. It's a differentiator shown here. If you try this one is time invariance. It doesn't change. It satisfies these conditions. It means that if we applied xt, differential operator gives just the dx of dt at time t. But if we shifting the time t0, then the output d of dt x t minus t0. It's just if this is yt, then this one is yt minus t0. So just a time shifting version. So it satisfies the time invariance. You can try this one. This one, if you see here, time dependent one. This is time variance. Time variant system. This one is a little bit tricky. Okay, let's see this kind of this system. It means that xt applied to the system. This system replaces t with 2t, time scaling system, and yt equals to x to t, 2 times t. So this is these systems. Let's check up that this system is time invariance or time variance. let's try if we apply the signal like this one. This is t equals 0. And let's xt, let this one x1t is this one. This is 0 and 2, and this one is minus 2, and height is 1. This is applied to the system. And t replaced by 2t. Then output will be, let this one is y1t, will give x1 to t. Then it looks like this one, time scaled, so it's shrinking, minus 1 and 1 and this one. So x1 to t are given like this way. What about the time shift version? Okay, let's try to testing this one. 4, 0. Then this one is x1 t minus 2, time shifting version. We apply the time shifting version, then t is replaced by 2t. Okay, time scaled. Then it will shrink down like this one. This is 2 and 0, and this is 1. This is the output. So the output will be x1 to t minus 2. Okay, so this can be written in this way: x1t 2t minus 1 and this value. So t is just 2 times t. So this is it. But what about we check up here? Is this the same as a t minus, we shifted minus 2, so we shifting minus 2, then this graph will be given shifted 2 times, so it will become 1 and 3 like this one. So this one are not equal to this one, so it means that it's not time invariant, it's a time variant. It's obvious that if we try this one, t minus t0, then the output will be x to t minus t0 to t minus t0. You know what? T is replaced by 2t. T is replaced by 2t. But if you shifting the output, it will be shifting in this way: x to t minus 2t0. So this is not equal. So obviously this one is time variant. Okay. The third one is memoryless. The meaning is this one: system is memoryless if its output is depending only on the current value. But if not, it is memory system. Here the first one is a discrete time system: yn I equals yn minus 1 plus xn. But here this is current time, but this one is a previous one. So this one is a memory device. It has some memory. You can see here that is not current value, it's a previous value. So in somehow you need to keep this value in some storage. So it has some memory. But this example, output depending on only current input. So this is memoryless device. So this one is memoryless. So if in somehow there is some storage device that exists, it has some memory. So memorylessness is this one. The last one is causality. Causality means a cause and effect. There is some cause should be existed that output come out. So here shows that what does that mean? Output depending on current and the previous value, or the current and the past value. So here is a time sequence, and input is changing like that. If we measure the output at this time, then this is the input. All the current value and previous value means this is the current input xt, and the past xt is this one. Only past value affecting to the output. It means that the cause and effect, then this is called causal system. What is the non-causal system? Non-causal system, the future data affecting the current value. So this is the current time point, but the future data in somehow affecting the output response, that is called the non-causal. Usually non-causal function cannot be implemented. So this says that the previous data affecting to the output, so future data affecting the data, then this is called non-causal. But the current and the past value affecting the current output, then is called causal systems. Okay, we talk about 4 different system characteristics. The first one is the linearity. Linearity related to the additivity and homogeneity. If you're satisfied both of these conditions, superposition are working. I give you some typical example how to testing the linearity. The next one is time invariance. Basically, time invariance means that the system remains constant over time. If remain over time, then if you're shifting the input time like this way, then output is at the same time is shifted. Then this is called time invariant. So the next one is memorylessness. If there is some memory device, then system has some memory. But if system output depending only on the current value, then is memoryless. The last one is causality. Causality means that the output depending only current and past value, then it is called the causal system. Causal system means there should be cause that the output to come out. But the non-causal system, the future data affecting the current output in somehow, then this is called the non-causal filter. You can think about the non-causal filter cannot be implemented in usual way. Okay,